Is Sarah logged in already or?
I don't see her logged in. I know she's busy with travel, so
Okay. Okay.
Masha, is there anyone else in the waiting room or are we
Nope.
slowed down?
And yeah, we're slowed down and people can start joining if once they log on. So we're good to start.
All right. Yeah, let's go ahead and get started. I think you know, it's the day after Memorial Day, so I don't blame people for maybe taking today off and all that. But nevertheless, for those of you who are joining, thank you so much for being here. Appreciate you taking the time. Today, I have the pleasure of introducing Baijun Tian from the Jet Propulsion Lab. And he's going to be talking about a proposal we just submitted on using air-based global ocean surface turbulent heat fluxes. So Baijun, feel free to take it away.
Yeah, thanks for inviting me to come this webinar series to discuss this idea. So, and also know Professor Sarah Daly. I think when I was a student there, she already was a professor at Scripps. So I get my PhD from Scripps Institute in Oceanography. So I know Sarah. So yeah, today I talk about the AIRS-based global ocean surface heat flux product, and so we all know the global energy budget, the Earth received the solar energy from the sun, absorbed by the ocean surface, then radiated back in infrared radiations and cooling surface. But also surface is cooled by the latent heat flux, the synthetic heat flux, and the heat, the atmosphere. The ocean surface turbulent flux include the sensible heat flux, latent flux, are major components of the ocean surface heat budget, an important Earth system data record. And a lot of effort I think this group have known well, a lot have put in to develop the high quality, the graded, time dependent global scale ocean surface heat flux, his surface heat turbulent heat flux data set. And unfortunately, the direct measurement of the ocean surface turbulent heat flux is very sparse and very limited, particularly in the Arctic and Southern oceans. Right now, these flux are usually estimated using a bulk aerodynamic formula algorithm, especially in ice-free oceans. For example, the sensible leading flux is a product, is wind speed, is AIRS temperature difference. TS means sea surface temperature. T sub A is near surface temperature. The near surface SST and near surface temperature and wind speed determine the magnitude of the sensible heat flux, while the latent flux is measure sea surface and air speculative difference, QS minus Q sub A, and also determine wind speed. Those are the bulk formula. In these two formulas, only 4 variables are independent variables. So with this T sub S, sea surface temperature, W is the near surface wind speed, T sub A, the near surface air temperature, Q sub A is the near surface humidity. All other variables, including the transfer coefficient, C sub H or C sub E are determined by these four variables or specified parameter reasons. As a result, in order to improve the ocean surface turbulent heat flux estimate, we have to improve the estimate these four independent physical variables, the T sub X, W, T sub A, and Q sub A, these four variables. So there is several sources of these four physical variables. Usually come from three sources or combine of them. First is the in situ data from the moored buoy or marine surface weather report from the monitoring observing ships, VOS. Second is the numerical weather prediction based analysis or renaissance product. Third is a satellite remote sensing data product. So based on the different sources, this surface heat flux called different source-based ocean surface flux products. And different data sources offer very different spatial coverage, different spatial and temporal resolutions, also unique bias uncertainty of the ocean surface flux dataset. Yeah, first I'll talk about moored buoy. This is right now there is a lot of the moored buoy network. There is several buoy network in the tropical oceans. For example, the red one is called Caruso Extension Observatory, mainly from the near Japan. And the blue one is called National Data Buoy Center, NDBC, in the Northern Pacific, East Pacific, and Northwest Atlantic near coast of the America. These regions. The green one is called Ocean Sustained Interdisciplinary Time Series Environment Observation System, OceanSight. One is the North Pacific, one is the Southeast Pacific. Also, well known is Precision Research moored buoy in the tropical Atlantic in this region. Also, Rama in the Indian Ocean, and Tor and Triton in the tropical Pacific. Clearly, you can see from the maps, those buoys have provided accurate measurement of these four variables, but they are only limited in the tropical oceans and have a serious spatial and temporal sampling problems. Then, for the marine observations from VOS, is mainly from the ICOS dataset, so-called International Comprehensive Ocean Atmosphere Dataset, ICOS. This dataset is a basis for several climatological flux product have used a lot. But unfortunately, this have a bad coverage in the northern hemisphere mid-latitude, especially during the fair weather conditions. Especially in the ship track regions have high coverage. But in the southern hemisphere, especially southern oceans, have less coverage, have poor coverage. As a result, also they have sampling issues. Some regions, especially in the poor sample regions, sampling bias can as large as 60 watt per meter squared. The second data source for the heat flux is the analysis or renaissance dataset. This kind of data sets is good. It's globally and graded and easy to use. But we all know numerical models, reanalysis based on numerical models, they have a large uncertainty due to imperfect preparation of physical process. For example, for the older generation reanalysis, such as inside recurrent reanalysis or ERV40s, the latent flux in this data is these two reactors can differ about 100 watt, which is huge. The state of art new reanalysis has ER5, MERA2, CFSR. I think the error is much smaller, but smaller than the old generation, but still large. Then the good thing we have satellite data. Satellite based on several satellite-based ocean heat flux has produced in the last few decades. And the good things about satellite data is they have a high spatial and temporal resolutions and global coverage. And these are the best coverage available, has extended used by the community. For example, one dataset is called HOPES, Hamburg Ocean Atmosphere Parameters and Flux from Satellite. Japanese group, Japanese ocean flux dataset with use of remote sensing observation. Jeffuro, I don't know how to pronounce that. Also, NASA Goddard using a Goddard satellite-based surface turbulent flux, GSSTF. And the French group have IFREMA, I don't also C-flux from Dr. Curry et al. And Claes et al. And OA flux produced by Dr. Li Sanyu. And Cygnus also provides its own flux data with developed by Huang. And however, if a lot of studies have studies in the comparison of the satellite ocean surface turbulent flux, and lots uncertainty, lots difference exist among those satellite data set, and significant uncertainty still exists in this data set. For example, Bronk et al. 2011 compared ocean surface turbulent flux from 11 different global flux data set, and they found the bias can be as large as 6 or 20 watt meter per square for sensory flux and latent flux respectively. Bantemi et al. 2017 evaluated the daily ocean surface turbulent flux from the major satellite based and reanalysis-based product. And mostly also have the similar spatial patterns and spatial time series, but significant difference in terms of magnitude among those datasets, especially in the West Ocean boundaries in the Northern Hemisphere winter seasons and high southern latitude. And the difference among these datasets can be about 30 watt for latent flux and 7 watt per meter square for sensory flux. And if you look at data source for the 4 independent variables, there is a lot of data source. I list a table, talk about the data character for this, all the satellite data set and the bulk formula used, and data source for sea surface temperature, data source for the near surface wind speed W, data source for near surface air temperature, near surface humidity. And different data use different sources. That's why I think the satellite estimate these 4 variables are the key to understand the uncertainty of the satellite-based ocean surface flux dataset. And for the satellite measurement surface temperature and near surface wind speed, this dataset has been already available since 1980s. This dataset usually have a relatively long, a reliable time series, and it's good. The uncertainty is much smaller in these two variables. Yeah, for example, the near surface SST product moves from the infrared radiometers such as AIRS, MODIS, AIRS, or microwave radiometers such as TMI, TRIM microwave imager, GMI, global precision measurement microwave imager, or MCE. Or satellite-based near surface product, either from the microwave scalerometers or microwave radiometers or even thickness. So these two products usually is pretty reliable. However, for the near surface air temperature and near surface humidity, the satellite estimate still have a lot of technical difficulties, because usually from these two variables, especially for water vapor, based on the total column water vapor, the measure radiance from the relatively thick atmosphere, and retrieve is the near surface humidity from the thick atmosphere is very difficult. As a result, satellite-derived T7A and Q7C have lots of uncertainties, and major source of the satellite-based ocean surface temperature flux is mainly from the inaccuracy of the satellite estimates of T7A and QZ. This has been demonstrated for many studies. Just list some reference here. And yeah, for example, for the satellite measurements Q7A, basic idea is from the total column of water vapor. It's started by their work, Dr. Tim Liu and Peter Nealer in 1984, in the 1980s. So basically tried how to relate the total column water to the near surface humidity. And in the last 4 decades, there is probably 3 stages of this retrieval. First, by the work South et al. 1993 and Cho et al. 95-97, who basically using SMI measurement to first determine the water vapor in the lowest 500 meters of the atmosphere, basically some boundary layer water vapor, then retrieved near surface and Q7A near surface humidity. So the basic idea is near the boundary layer water vapor is mainly related near surface humidity, linear relationship. Then the next is in the 1995, Sousa et al. Further improved those methods, proposed a method direct Q7 retrieval based on the 5-channel SMI barometric temperature, which is better than the 2-step procedure of the Sousa et al., with literally improved Q7 retrievals. Then later on, people tried using animal sounding data, such as from the M3 AIRS, SMMT, because sounding data give you water information, can help retrieve near surface temperature. Several work there. And and if you look at the satellite estimates T sub A near surface air temperature, some study estimate sub A from the surface temperature based on some assumption of the constant air-sea temperature difference, or based on near surface humidity retrievals using assumption of specified relative humidity. As a result, this estimate have big errors caused by the ad hoc assumptions. For example, Liu et al. Liu 1988 estimate T sub A from Q sub A, but just assume 80% relative humidity. And Hobbs for flux data estimates T sub A from SST. You assume 80% relative humidity and 1K LC temperature difference. And the French flux data assume 1.25 degrees LC temperature difference. Another method, some other studies just using renaissance near surface air temperature directly. If, for example, the SSTF Goddard heat flux and Japanese heat flux using instead of DOE renaissance product, and OA flux using instead of DOE and EI 40, and Cygnus using Mero 2 and EI 5. So since there is such large certainties for the satellite measurements T sub A and Q sub A, and that's the major sources for the satellite-derived ocean surface flux dataset. And that's why we can see using different sources, using different retrievals, T sub A and Q sub A, to improve the ocean surface flux product. And that's why we are coming from the AIRS data. So AIRS data is on the NASA Aqua satellite. Aqua satellite, Aqua means water, the satellite was launched in the 2002, May 2002. It's a sun synchronous near polar orbit. It's 1:30 a.m. p.m. ascending descending orbit. See, can show some animations. So the polar orbiting polar orbiting orbit, and so right now is about 23 years already, and there is several instruments on the Aqua satellite, such the AIRS, MSU series, MODIS, MC, basically measure all the water-related variables, such as solid, liquid, gases, formed water, both over the land and the oceans. And AIRS, the so-called AIRS MSU sounding system, AIRS means atmospheric sounder, along its partner instrument, advanced micro sound unit. MSU, MSU is a temperature humidity sounding system on the Aqua satellite. So, so AIRS is the 2,378 channel grating spectrometers to measure infrared radiance at wavelengths in the range 3.7 to 15.4 micron, with horizon about 13.5 kilometers at nadir, while MSU is a 15-kilometer mercury radiometer with a horizon about 45 kilometers at nadir. So this both the crossing track scanning media sounders have a swath roughly 1,650 kilometer wide. Is this two collocated, aligned, or work together? So these two independent work together through the both infrared and macro channels through cloud clearance cleansing algorithm can provide accurate measurement, temperature, water vapor profiles, as well as near surface temperature, near surface humidity, and sea surface temperature, which basically is a horizontal resolution about 45 kilometer. The temporal resolution about twice daily, and ascending, descending, afternoon, and evening orbit, and almost all sky conditions for cloud cover up to 70%. I think those data sets, as near surface temperature, humidity measurement, they're particularly important in Arctic, Southern Oceans, where the in-situ observation is very sparse, and also cloud is prevalent. So this, although is a sounding data set, is the main product has been using widely, but the surface product has utilized. But we think we have good opportunities, and we think the AIRS M2 combined retrieval near surface humidities may be better than previous microwave imager, such as MRI-derived Q-sub-A, because the AIRS M2 have both infrared sounder and microwave sound informations, and have more informations for the near surface humidity. That's why probably should have a more accurate estimate. Similarly for the near surface temperature, because have the water information, temperature informations, retrieve near surface temperature should be better than those based on satellite near surface temperature or near surface humidity or from the renaissance. And that's why this can be good way to improve the ocean reflect product. And actually, there is several studies have explored the potential of the AIRS data for the ocean surface flux product. The latest work is by Dr. Sinfudong and Dr. Sarah Gailey, published in 2010. They assessed the potential of the air surface temperature humidity in turbulent flux estimate. And for example, these four figures, I think the left column is sensible heat flux, right column is the latent flux, is up two panels is sensible latent flux. The red is based on in-situ observation seabound. Blue is from inside Inca Renaissance. Green one is from the AIRS. And this light blue from MCE. And this is for sensitive flux, and this for latent flux. And is from the satellite data product together. So the work, you can see their conclusions, AIRS data can produce the ocean turbulent heat flux estimate that are accurate enough to study the climate variability in the southern oceans. That's the main conclusion. Also, several studies by Dr. Buswell, several papers and also Taylor et al. 2010. They also demonstrated the value of the AIRS within 5, within 6 data in deriving the surface turbulent flux in the Arctic regions. And for example, this paper, they show the the yearly moist flux, basically latent heat flux anomalies in different years. And the pink color means more moist flux, blue color is latent flux. You can see the AIRS data can give a realistic variation of the moist heat flux in different years. And also, from Taylor et al., there is a paper in the Arctic regions, in different regions, their annual cycle shows the annual cycle of the AIRS in different regions. And this annual cycles is more realistic than other data set. So this have some promising data set. That's why we try to produce the AIRS-based ocean surface turbulent flux product. Basically, what we thinking using the bulk formula using Tau core 3.5 bulk formula. This formula is based on the Morning-Obikov similar series using. Hello? Somebody have question?
I think someone just had their microphone on, so please
Okay.
remember to mute your microphone.
Okay. So I'll continue. So this formula using stability, height, atmosphere, wind, and pressure surface gravity dependent turbulent exchange coefficients for the surface heat flux, latent flux calculations. And this is a very mature algorithm using extensively for the AIRS interaction communities, such as Cygnus flux flat used by Huang et al., Crossby et al., 2019. And for the near surface air temperature, humidity, and SST data, we're using AIRS 1.7 standard level C product basis 1 degree by 1 degree spatial grid on the daily temporal resolution starting 2002 and based on the AIRS AMSO combined retrievals to the September 2016. Near surface wind speed product W, we tried using remote sensing system cross calibrate multi-platform CCMP version 3.1 product. This ocean wind vector analysis product is on the quarter degree by quarter degree space grid. This is the level 4 product. And on the global, I think the global oceans is this combined surface wind retrieval from multiple satellite macro sensors and the background background field from the renaissance on the 6-hourly temporal resolution. Yeah. Based on this, we can generate the AIRS AMSO-based ocean surface flux on the daily, monthly resolutions, and also the uncertainty on the global ice freeze oceans on the 1 degree grid from the September 2002 to September 2016. The reason we stopped September just because that month the AMSU stopped working. So after that, just infrared only. So the quality may not as good as the AIRS infrared plus microwave combined retrievals. Then we can, after calculating, we can compare, we can validate this flux compared to those calculated from the buoy data set, ICOA data set, we can also compare this kind of available satellite-based data sets and can compare how much better the AIRS data compared to other satellites. And we can use in the in-situ data as a reference. And since this data is stopped September, we can extend data to the parent using the CRIS ATMS data from the from the NOAA satellite, because in different instruments from NOAA satellite can extend for her. Also, AIRS not have a ice-free ocean coverage, can have a global ice covered oceans have some data set, can extend the ocean surface flux from the ice-free ocean to global ice covered oceans. I think that's a benefit of the data set. The ideas is provide this daily, monthly data set, daily global ice-free and ice-covered oceans 1 degrees from 2002 to present, and which is another satellite data set complement existing satellite-based ocean heat flux product. And so in summary, so basically the current satellite-based ocean surface turbulent heat flux are the best flux data available. The main source error sources are the satellite-derived near-surface air temperature T sub A and near-surface spectrum wind Q sub A. The AIRS MSU, the NASA temperature humidity sound system, have provided improved global measurement and near-surface air temperature, near-surface air humidity at high spatial temporal resolutions, and we can use it to produce AIRS-based ocean surface heat flux dataset over global ice-free oceans with a daily temporal resolution and 1 degrees resolution from 2002 to 2016. Then this can be extended to global ice-free oceans, global ice-covered oceans, and to the present using CRIS ATM's data. And this data can enrich the existing satellite-based ocean surface turbulent heat flux dataset, help the climate community to better understand the AIRS interaction and climate process hydrolysis cycle. And that's all I try to say. And I welcome your comment, questions, suggestions. Thank you.
All righty, thanks, Baijun. What questions do we have for this presentation? Feel free to raise your hand or go ahead and unmute yourself to ask a question. I'll ask a quick one here. More of like a hypothetical brain. He's not like an exact answer. So we're talking about using AIRS AMSU from 2002 to 2016, and then CRIS and ATMS after that. What would you expect if this gets selected? For the CRIS ATMS Fluxes, how do you think that would compare to the AIRS AMSU? Would it be like a similar resolution? Will we see improvements in there? What would you expect if we were to transition from between the AIRS AMSU Fluxes to the CRIS?
These two data, the AIRS CRIS have very similar characteristics, just a different satellite platform. Okay. So the spatial temperature all will be the same. Yeah. And right now, it's 1 degree, 1 degree. I think we can increase the spatial resolution to half degrees. And yeah.
Okay. Any other questions?
I know there's a lot of experts here.
Yeah. Well, and if I ask questions, it's a conflict of interest since I'm also on this project. Um, yeah. Can you remind me again how we're, because we're focused on the ice-free areas here. So I can't remember if just mentioned in this, but how are we detecting when there's ice present in order to, make sure that's flagged out, and the fluxes are not estimated using this algorithm?
I think there is CI's concentration data set can identify why there is ice free
Mhm.
or ice covered. And the bulk formula have to modify a little bit in the ice cover regions to include ice cover features. So, but it's similar, but a little bit modifications. So.
All right, thanks. Megan, we see your hand raised. Go ahead and ask your
Yeah,
question.
thanks. Well, great to see the kind of overview of all these different satellite-based products. So I didn't quite, yeah, if you can go back there. When are you doing this already? And also, so, I mean, is this product now available or are you just proposing to do this?
We are proposing to do this.
Proposing to do that. Okay.
Try to get
And
some funding to do the work.
all
Yeah.
right. And what would be the temporal and spatial resolution of this product then?
Yeah, this is a list here in this one.
Oh, I
Is
see.
is a daily
Daily.
is a daily data set. It's
1 degree, 1
from
degree.
Yeah, yeah. But we can increase the half degree, 5 degree. Yeah, because the level 2 data set is 45 kilometer. It's close to half degrees. Yeah.
Okay. All right. Very good. Good luck.
Okay.
Thanks.
Thank you.
Rick, go ahead.
Yeah, hi, thanks. So the uncertainty is in the atmosphere, certainly in the variables in the atmosphere. Is there an element of the project that focuses on uncertainty in the heat budget in the ocean at all?
Yes, try to estimate the uncertainty of heat flux, both sensible heat flux and latent flux.
Sure. I mean, some of the initiatives on the screen focus on constraining the ocean heat content to some extent, and that, since you are looking back in time a little bit, you could look at the sort of mismatch in the estimates of the ocean heat content, perhaps.
Ocean
It
heat,
would be, yeah, it would be a side project, of course, but it might be interesting.
Ocean
I don't
heat,
know. Yeah,
that's very interesting.
it is. It is a highly in need of constraint, in need of constraining aspect of the total ocean atmosphere heat content. Yeah. Anyway, just a thought, just a comment.
Thank you for the suggestion.
Sure.
Yeah.
Any other questions? All right. If not, I guess we can go ahead and wrap this up. So, Baijun, thanks again so much for presenting here today. And then we will see you all next week.
Okay, thank you for your invitation. I'm glad to present here. I'm glad to see everybody here. Thank you very much for your interest.
Thanks again.
Yeah, I stop sharing then.